Yes, this video is going to be about, let's say, a project, a template project that's going to be used in this course. And the template project is some pre-programmed functionality that's going to be used for the exercise partially, and some are in there for examples. But they also described in the compendium. That if we look a little at the compendium first. Let's see, here in 4.8. So this is what's included in this template project, or project template, whatever you want to call it. There is an analog input scaling function block. The blue ones are function blocks, the green ones, they are functions. So we're going to look at this online, not online, but in the PLC. But they are described down here, the various blocks. There's one for input scaling of analog inputs, or scaling of analog inputs, and descaling of analog outputs. And then there is a filter included here, the first order exponential filter. A bistable emulator used to simulate a bistable actuator, for instance a valve in the field or motor. This one is going to be used for one exercise. There's a pseudo-random-number-generator, that's also for simulation, and that one is based on this random number generator here. This random number generator is going to be used in one exercise. This is what's been talked about in earlier videos and earlier in the compendium. This function checks the validity of a long real or double number. And here is the counterpart for a real or single number. The first scan is going to be used in the exercise, and the first scan, what it does is it tells you that now the PLC has been restarted. And the getLongTimeTck is going to be used in the exerciser. That's based on this one. You could use this function or this function. But this function here, the L-timeTck, takes more processing time because it actually performs the calculation to get this long time tick. The fcLongTimeTck gets its long time tick, the nanoseconds, out of a data block that this one uses, or this function block populates. So put these values into a data block. This function put this long time tick into a data block, which this one reads. So this is just getting the long time tick, which is prepared by this one, and it is this system function that's doing all this stuff. And save system data is used also by this system function to save the system data in a data block. And the last one, the runtime, is a program that can be used to calculate or show how much time or how much processing time a program uses. The descriptions for the blocks, each of the individual blocks are down here. This is left as an exercise to just read through and read what it says. So what I'm going to do now is that, maybe I should move over here. Here is what we call the project template in real life. It's also running here as a simulator. Now I've got two of those running. That's for another project. So then we are going to look at the blocks. I'm just going to open these. They are know-how protected. If you forget the know-how protection password, that's the last time you look at your block. Here is code for this one. It's not that involved, but it's a little involved. What we're going to look is just the inputs and outputs and what it does. So basically what this function does is that it takes an analog input here, which is a number between 0 and 27648. It has a fault input if you have a little faulty. This has to do a little bit with the filter, because it has a built-in filter with a time constant. This is a first order exponential filter. Same algorithm as this one. And that needs a samplings time. Samplings time, and this one just tells that okay, this function blocked instant is running on a cyclic interrupt, and then this then the cyclic interrupt would have to be 200 milliseconds for this to work, if it is. The high range engineering units that output the low range, and there are some error limits, because for the analog input of a schematic module can go, it's 27648 as maximum, but it go all the way up to 32,767, whatever, over 32,000, which is called overrange. So you get an error. The YF is set to true if you go over engineering's unit by 5% or below, which is called overrange. That was the filter. This division factor is in case you use a resistor input. The division factor is either 10 or 100, dependent upon if the analog module gives you the result with 1 or 2 decimal points. And here is the type, unipolar. That's one-sided input, for instance 0 to 20 milliamps, 4 till 20 milliamps. Bipolar is two-sided, minus 20 milliamps to 20 milliamps. And resistor, then the number here is pre-scaled with 1 or 2 decimals. It's still an integer value. So a temperature, let's say if it's scaled with 2 decimals, an input of 1000 divided by with 2 decimals is 10.00. 1001 is 10.01 degrees. That's the temperature. Here's the output, and this is just internal, the internals of the function block. We're not going to look at all of this. Now I'm just going to open the output scaling. Instead of cancel, I don't give it a password, but what I can look at, first look down here, it's just the title of the block, and you can't see the code. That's the know-how protection. I could remove the know-how protection by right click. Where does it say? Once in a while it disappears. It's basically a right click. I would have to restart TI portal to get this back. Know-how protection, it should be down here. Okay. Let's see. There might be that the reason why is that the block is open. There, it was. Yes. Because I had opened the block, and then you can't. Here, it's just to write the old password and remove, and then the no protection is gone. But then again, if you forget your password, that's no one can open this block. That's function block. Analog output scaling. Here is engineering units. The maximum for the input, the maximum for the output, the type, unipolar and bipolar, two-sided, one-sided. And if you want to limit the scaling, let's say if I have 110, should then the output go over 27648? Yes, and then there's a fault if there's fault. And now the internals here, it doesn't have any input, but the statics, the internals that the other function block that we could see because I supplied a password, you can't see here. Yeah, I'm going to close that one down. The first order exponential low pass filter is going to do the same here. That doesn't have a no-hop protection. I'm just going to scroll through here. Here's the code. So this is the code required for a first order exponential filter. I'm going to show how to put on to no-hop protect this afterwards. But what we're going to look at first is the filter. The input, unfiltered value, the output, that's filtered. The time constant for the filter is the same as for the analog input scaling block. The sampling time is 0. This one would work with 0. Then it would just use the actual running time of your program, and a substitute value if the filter detects an error. If you this reset, if that's set to true, the input is just passed to the output without any modification. And then if there's a fault on the filter, and here are again the internals of the filter that's used for the code. Yeah, I should show you how to no-hop protect. Function is right click, no-hop protection, ask for password, something I can remember. And you have to confirm it, write it twice. If I did it correct, I got a padlock here and ask for password. Okay, and then I'm back what we had for this one. No-hop protected. Take some time to open this. So this is what is an emulator. This is something that you can use an instant of this function block to make a, let's say, digital twin for bistable control element. But what it basically does, it responds to what you program. So what this one do is that if this one is set to true, switch to high on level, then so initially this one is true, low state, because it switches just between two states. So initially this one is low. If the X input is set to high or true, the program waits for this action delay here, 500 milliseconds, then this one disappears, and then both are false, because this is what's telling whether this is high or low. Yeah, disappears, and then it waits for the transit to high delay, in this case 3 seconds, and then this YGH high state is switched on. If I remove or set X to false, the opposite happens. It waits, action delay too low, it waits 500 milliseconds, this one disappears, then they are both false, and after this time it's set to true. Now if I use this one, if I activate the FSH, it's going to do the switching as it would on the X, but it doesn't care about the X. And the same with FSL, it's going to switch it to low, no matter what the input X is. The force high just sets both signals high simultaneous. Force low just resets both signals out. So these inputs here, they are used just to verify what you're testing. The program you have made that controls a bistable element up and down, that's just used to test it for correctness. The next one generates a random number. This also has this with if it's called on an interrupt. This input is passed through, and then there is the output is just randomly altered based on a bias. Here you enable. If you want, let's see, if it's not enabled, the output is just passed through. No, the input is passed through to the output. Yes, and how often should this random output be updated? And then the random number is a number between 0 and 1, and here you say how much should you multiply this by. So the bias is what did I say? It's an offset, and this is, well, you can put a signal into this one, and if that signal is changing, you can add random values to that signal. So what you in effect can do is you can generate noise on this one, and these are square pulses noise that you get. So if you want to smooth those, you could use the first order exponential filter to smooth the squares. That's basically what it does. This one, what we have seen, the blue ones here, they are function blocks or classes. They need an instance data block to work. This one tests, that was the long real number. You have a long real number in here, and it checks if it's valid. This output YF is set to false, and the output is just passed through. The function, which is of type long real, then it's set to the value of the input. So the input is just passed out here. Now, if it's an illegal number, then this substitute value is passed to the output, and YF is set to true. The real number exception is identical, but for a single value, 32-bit floating point number, this long real is 64-bit. The random number generator, which is used, that's going to be used in an exercise. No, it'll open. It has a random number seed type long integer, and the seed is a prime number, or should be a prime number, doesn't have to, and for each time it's called, it outputs a new random number between 0 and 1, and the seed is updated. So the seed has an initial value, and this as this is a function that can't store values, this function has to store this value somewhere, and that could be a global memory or a user data block. This is going to be used in an exercise where the number is stored in a user data block. We had the real number we looked at. The GetFirstScan just returns a binary, so the function doesn't have any arguments. Yeah, it returns a Boolean value if it's true. Your PLC has been restarted, which means the power has been on off, or you have used a run stop switch to switch it on. And you can call this in your program. and if true, your PLC has been restarted, and if your program need to do something when PLC is restarted, then you use an if sentence, basically say if this function, or you return the value to a boolean, if it's first scan, do whatever you need on a first scan, because this one is switched high for a certain amount of time. You decide how long this restart indicator is going to be set. The long time tick again, read only. Just returns a long time tick. First of January 1990. The number of nanoseconds since that time. The save system data is used by fbSystem. That's not that interesting. Doesn't do much. The long time tick is used by the system function, as I said, to generate this long time, which is picked up by this getLongTimeTck. So yes. And the runtime commercial runtime. What we are going to look at is these programs here. This is a user data block that can be used. And here is program sections. And as in this course, these are the exercises. There are 6 exercises that should be programmed here. Here they are done. In the template, there would be and this IDB, the Morse decode, and they ask you to Morse function block these 2. And the program should be made and enter in here. This is just an example. So the exercise is the Morse encoder to program that. Here's the bistable control exercise, the use of this emulator, the Monte Carlo simulation. It's going just to estimate the number pi using Monte Carlo simulation. Uses the random number here. Square root extraction uses a Newton algorithm and program iterations to find the number, the square root of any number. And the first exercise is program instructions, if sentence or whatever. That's just to get to know a little programming here. Now there's a PLC running with this, and this idb system and db system, I'm going to open both of those. They are no-hole protected, and the reason the dbSys, I can give a pass. Open up. Try to remember my password. Nice luck. These are the system data. See, and as it's running, I can go online here and see. Switch on the glasses. Impossible function. Yeah, this I'm now online. This indication indicates that the block online and offline, they are not equal, and there's a no-hole protection. That is the difference. So if I just download to my CPU, I'm all good to go. If it makes this a little. Let's see where we have. This is a millisecond counter. This CPU has been running for 28 minutes now, and this is the long time tick. There are quite a few days, 190,000. No, 19,000 days since 1990. Well, it was probably correct. We trust the program. And here is the cycle time, around 1 millisecond for my program. The program that is in here is not doing much at the moment, but it's doing all the exercises, executing all the exercises as a matter of fact. But they are not complicated, and they don't consume a lot of CPU power. Yeah, so that was the system data block, and here is the first scan indicator that's saved here, which is collected by getFirstScan, and this function just returns this value. And we could make a function too that will return this value if you wanted to. That's left for you as an exercise. It's not difficult. If I got time, I could show that. Now we go to this. That was the instance data block that we are going to look at. This is the data that this function is working on. Here is something that can be useful. This one also has a restart output from this function block, and you can enable the outputs and enable cycle time measurement. Here are the same data as we looked at the data block. The system data is of a type. It's of a data type, and data type is this one. So the data block, the user data block here has a declaration of this type, and also this function block has this. This data here, the structure user data, they are just saved in the data block here. Okay, so this is the instance data block for the system function restart. We're going to look at this shortly. Enable outputs. I just double clicked it. I say switch that to false, and then these outputs they stopped. Switch them on. I have to hit. Then that's the cycle time measurement, and now the outputs turn back on. So these are two square wave signals. The first square wave is it's alternating, or the frequency is a high and low. Duration is 625 milliseconds, and the other one is 1 second. This duration here is defined as something called fast flashing, and the 1 second you could use that for timing. It's just count, and every time you count, that's 1 second. You will need to make an edge test here. That was the cycle time. That's output here from this. So this is the system function. It doesn't do much, but it does enough. It provides some, let's say here, timing, first scan, and some time, some square wave pulses that you could use. So what we are going to look is here in this task background and task restart. They are not know-how protected. Could be, because let's just see what they do. What this task restart, the only thing it does is call the instance of the system function and says restart is true. And when we get to the program, let's say the task background, which is this cyclic program, also uses the system function here. Then it says okay, because when your CPU starts, then this task restart runs, and then after that the cyclic program is started. But you might have time control programs, or programs, for instance, in the cyclic 5 milliseconds, and then this restart indicator should stay on for some time. So all your cyclic program, whatnot you have that need restart, can pick up the restart. If you set this one to 0, then the restart indicator is just for one program cycle down here. Yeah, so that handles the system and also this timing, the getLongTimeTck, and this is provided when this one is called. The rest of this background task is the simulation program that you put in. There's going to be one simulation program in here. It's the exercise. This one needs a simulation program, and that runs outside this function and measure how long your main program, what you program here, how long time execution time is that program. So in the exercise, when I'm working on this is where in the program main is where you enter your program. Let's say, okay, here, these are all the exercises. It's a program for each exercise. That's called, and the simulation, which was again called in the task background. The task background is a background task running cyclically. When it's done, it restarts all the time. And there's only one simulation here, and that has to do with the exercise here. So these function blocks that are in here, we are not going to use all of them that are in here, but it is possible to use them for yourself if you want to make instances of the function. So what we're going to use is the random number function and this emulator. The rest is in here for just to show some example of function blocks, and they are also then again given a description up here in the compendium. So I just talked a little about them, but here they are described to or brief to the description. Yes, that's would be about it. Okay, so let's say for this course there is a project template that contains some functionality. The most important here is it has a function and a function block that is going to be used in the exercise, but the most important here is that the system is organized. So when you do programming, and here you have to enter the program you make into a program called prgMain. And if you have some simulation, you have to enter the program in there. When for each of the exercises, there's going to be a video per exercise describing the exercise and also showing here as an example what kind of program elements should be made for the exercise. Yes, so we're doing the exercises I'm working on in this course. There is going to be two simple programs, videos for two simple programs. They are not exercises. Those simple programs will be made in this project template. And the reason why is that if you have to insert a new CPU and make a new system and these functions from scratch, you need a certain basic functionality in a PLC. So this is absolute basic functionality that is required, some timing and a restart indicator that's provided by the system, and it also organizes the program for you. That's one way to organize this program. Contains some library function and the program section. The library that's there for you to use as necessary, and the program has tasks and main program organization units for where you can put your program in, and that's about it.